Dr. Shane Dooley was about simulating collision models and unitary circuits using primarily Qiskit, IBM's quantum software that will help us throughout this simulation. So a quick brief overview of what I'll be talking about and like the order is first I'll be going over what are the collision models, what is the brickwork circuit that I'll be using, the unitary gates and how we compose them, the results of what we found when comparing the two, and the future goals after this simulation. So for the collision model, we first start thinking about a quantum bath B and a quantum system inside that bath. And looking at the the system qubit row alongside the environmental qubits represented by these etas, we look at the system and the bath in a joint state. So each of these environmental qubits are going to be assumed to be in the maximally mixed state, which is the identity over 2. And it is very important to note what kind of collision model we are really working with. We are going to be using the Markovian collision model, where the environment does not interact with itself. Environmental qubits are initially uncorrelated, and each environmental qubit collides with the system only one time. So on the left and right, you can see a pictorial diagram of these collision models. So on the left side, kind of hard to see, but your environmental qubit, after it passes through your unitary gate, it's cut off and does not pass through the second unitary gate, representing the fact that each environment only acts on the system one time. And on the right is the exact same thing. Your system acts on one environment with one gate, and we're going to be using the same gate each time before discarding that environmental qubit. Now, a density matrix, which is what our system qubit is going to be, evolves through a unitary gate through the matrix multiplication of the unitary times the system times the unitary's adjoint. And through this evolution, we could start to form the quantum channel that is going to be our main focus throughout both models. So as we are not using the environment again, we could form a partial trace over the environmental qubit to form the channel, where it's very key to note that in the collision model, we are removing the environment and keeping the system as it evolves. So here is just the representation of what happens after n collisions. So we see that as the state goes through n unitary gates with n environments, each time we're removing that qubit that we don't need. And through studying the effects of the quantum channel, we can keep track of the block vector that governs our system qubits and study how it relates to the brickwork layout. So what we first want to do is, on our simulator, create a random pure state using Qiskit. And since it's a pure state, it will rely on the block sphere with your block vector magnitude equaling 1. And here I want to mention how we are generating our 2-qubit unitary gates. In the simulator, we could use the Cartan decomposition, which takes in 4 different single qubit unitary gates, and the non-trivial function being the exponential with 3 parameters times your Pauli matrices. But I want to take this moment to mention a future plan of the project is to start using quantum hardware, and these parameters that generate our qubit gates aren't easy to be used on a quantum hardware, as there's a limited amount of gates available. So oftentimes we'll have to find a workaround using rotations around the Y and Z axis. So right now, I want to also mention the brickwork diagram, which is going to be our other model. As you can see on the left, we are stacking these unitary gates, where the red is the normal unitary, the blue is the adjoint, and we have one system qubit in the middle of one. Now, due to the fact that these are unitary and our environment are maximally mixed, which is the identity, we could realize that the system simplifies itself, leading to this light cone shape. So the dynamics simplify due to the unitary structure and matching environments. And now I want to move on to the other quantum channel that we are interested in. So in contrast to the collision model, the unitary brickwork circuit evolves by tracing out the system qubit at each step rather than the environment. So as you can see with this channel, the partial trace is eliminating the system, and the evolution is then again captured by the quantum channel acting on the environmental qubits. Again, I just wrote out the what the future state of your system would look like after n interactions, and we could tell straight away that the dynamics of both models follow in very similar fashion. So to get a theoretical approach as well as the simulating approach, we wanted to express our quantum channels as a matrix acting upon these vectorized density operators. And to do that, we use the Liouville representation, where in my case, I use the orthonormal operator basis being the normalized Pauli basis. And then through this, we calculated and evaluated the channel matrix M, defined by the trace of the basis times the channel with a different corresponding basis. So upon finding this channel, we then look at the vectorized density matrix here, and we could find that we can compute a future step of, or a future evolution of our system by acting upon this channel matrix onto our initial state. Now, we weren't using unitary gates within our simulations. We were specifically using these two unitary gates, which are a subset of unitary gates that are not unitary in just the time direction, but also the space direction. They satisfy this reshuffling condition, and I just wanted to show, due to that brickwork layout diagram, what it really means. So on the left side, we see that we have our inputs and outputs, and in the middle, we're looking at our inputs I and K going towards the space direction, and we get outputs L and J. And for the right side, we have the time direction where our inputs are I and J going towards the outputs K and L. So if you have a adjoint to this matrix on the left, right, or top and bottom, you're going to have the identity. So again, to parameterize these to run it on a simulator, we use a very similar decomposition where we have a phase factor. Our single qubit unitary gates are now special unitary gates, and our non-trivial function has become something else, where before, where it was parameterized with alpha, beta, and gamma, we now have alpha equaling pi over 4, beta equaling pi over 4, and your new factor J. And so these gates allow for solvability and information propagation in both time and space directions. So I decided to fix a gate to compare across both of these models. So while messy, this gate gave rise to a very steady decay in both of the models, depending on what we will apply after. So at each step, we use the same unitary gate as shown. And using this gate, we defined the eigenvalues of the channel matrix in both the collision model and the brickwork layout case. And through this, we then studied what happens after we apply a swap gate after this unitary, as we'll notice how similar the quantum channels are, and we're just trying to see what happens if you swap the environment and the system if we're partially tracing out one or the other. So this table shows the eigenvalues for that Liouville representation matrix, where we have the 3 eigenvalues for the collision model being shown, and then upon applying a swap gate straight after your unitary gate, your brickwork diagram gets the exact same eigenvalues, while your counterpart has just 0 as your eigenvalues. So to find the predicted purities per step, we looked at the block vector representation. So looking at the purity, we found the trace of rho squared to be equaling to half times that should be the identity, I think, plus the block vector squared. And upon repeated applications of your quantum channel, the block vector evolves linearly with your block vector at your nth step equaling to your channel matrix to your n times your initial block vector. And the reason why I'm using a 3x3 instead of the 4x4 we found earlier was that your eigenvalues that you find in your channel matrix will always have one of them corresponding to 1. You get 4 eigenvalues, 1 being 1. And that is just kind of representing your identity in your block vector representation. So it's not really important at all. And we're mainly interested in the block vector just to see how it evolves. So therefore, the purity after n steps becomes half times the identity plus your matrix, channel matrix to the end on your initial block vector O to the power 2. And then if m is diagonal proposal with eigenvalues 1, 2, and 3, and your initial row vector in the eigenbasis, then we could calculate the purity as given. And upon looking at the two, we find that we have an exact copy of each other, depending on what gate we are specifically using. So on the left side, we use just the unitary gate that I showed earlier. And on the right, we use the unitary gate and then applied the swap gate and looked at the purity of both of these models. And we see that both of them match perfectly, which is great. That's what we predicted as well. And the dotted lines are the predicted results using the channel matrix. Here, I'm also going to show the block vector evolution. So as we can see, they both match. The top components match with the bottom components, depending again on which exact gate we are applying. And the reason why, let's say on the top half, your red line instantly goes to 0 is due to those 0 eigenvalues that we found with that channel matrix. So upon looking at our results, we see that the system dynamics are the exact same upon applying a swap gate after the unitary gate, and that the Liouville representation and eigenvalue analysis give a powerful way to predict and understand purity evolution without fully simulating the full density matrix. And so we now have a working simulator for both the collision model and the brickwork circuit. And from here, I just want to mention like some of those future plans that we hope to have achieved, but we did not have the time. So we aim to implement both the collision model and the brickwork circuit on real quantum hardware. And this involves adapting to the native gate sets that I was mentioning earlier and trying to mitigate any hardware noise through error mitigation techniques. And then Another point of interest would be the light cone dynamics on that brickwork circuit. So looking at how correlations and information spread within the light cone. And this could include quantifying the speed of entanglement growth and its dependence on the channel spectrum. And how this relates to the collision model is what we are trying to search for. I believe that is everything. Yeah. Is there any questions?
I have one question.
Yeah.
So when you mentioned the hardware realization, so what kind of hardware is it? What is this IBMQ?
IBMQ has like a set of native gates like available. Like some quantum hardwares don't have like the control NOT gate exactly available, which would pose some issues because swap gate is not available either. And if the control NOT gate is not available as well, then it becomes very tricky to start forming these 2-qubit unitary gates.
And how they're usually like realized in this hardware? Do you know?
I'm not too sure.
Different ways.
Sorry, what do you mean?
I mean, how they physically don't know.
I believe it has a lot to do with condensed matter theory, but I'm not too sure.
Okay, superconducting qubits, superconducting circuits.
Yeah.
Thank you.
Yeah. Oh yeah, sorry.
If I understood you correctly, you look like this, you tested the set of ideas for the one qubit case.
Yeah, for the one system.
The 2-qubit case and you for symmetry. How difficult is it to test it? That's it.
So like if you have two system qubits, or
yes,
I reckon it wouldn't be too hard to calculate for any steps that doesn't involve them interacting. And upon the interaction, for like the brickwork layout, if I can show you. I don't think it's sharing anymore. For the brickwork layout, I reckon you'd see like 2 light cones and eventually they would interact at one step and we would just look at that second qubit system. And we're probably just, if we're interested in the first one, we'll trace out the corresponding one. So in the brickwork layout, we trace out the system we're looking at. So we would have the second system moving on forward, I believe. That works.
Okay, so no more questions. Let's thank our